An ice cube floats partially submerged in a glass of water. The ice cube melts. What happens to the water level in the glass? So it's either going to stay the same, or it's going to go up, or it's going to go down. But weirdly enough, the first question we can ask ourselves is this ice cube accelerating? So our answer should probably be no. And that's going to tell us something about the net force on this ice cube. So if we think about Newton's second law, we know that acceleration is zero. We know that F net will be zero. So now maybe we want to think about the two forces on this ice cube. We're going to have a weight force pointing down and a buoyant force going up. And they're going to be equal in magnitude. So FB is going to equal W. And we want to ask ourselves, well, how can we figure out the volume of water displaced by this ice cube? And how can we figure out the volume of water added when the ice cube melts? So let's first think about the volume of water displaced by the ice cube when it is floating. So we can plug in here. We know that weight force is going to equal m times g, and buoyant force is going to equal rho v g. And so rho is going to be the density of the fluid, and v is going to be the volume of the fluid displaced. So we want to find this v, and just get rid of these g's. And this, of course, is the mass of ice here. And we can solve and find that the volume of water displaced is going to be equal to the mass of the ice over the density of water. Okay, so now we just need to figure out how this volume of water displaced compares to the volume of water that will be added when the ice cube melts. So we know the mass of the ice, and we know the density of water. So if we know a mass and a density, can we find a volume? Well, I think so. And important to note here is that the mass of the ice, well, that's not going to change when the ice melts. The mass will be conserved. So the volume of water added is just going to equal the mass of the ice over the density of water. And so, of course, that comes from the density equals mass over volume equation. So we see here the volume of water added and the volume of water displaced both equal the mass of the ice over the density of water. So we can conclude that the volume added is the same as the volume displaced, and therefore the water level in the glass is going to stay at the exact same height. So we can summarize this by saying that when the ice is floating in the water, it displaces its mass in water. And when the ice has melted, it becomes its mass in water. So that's not a very interesting question. Let's think about if this ice cube is now floating in lemonade. So we've already done some of the work here. So let's just write out our equation. So buoyant force is going to equal a weight force again. But now for rho v g, we're actually going to have the density of lemonade and the volume of lemonade. So we know that the density and the volume are referring to the liquid that's being replaced, not the object floating. So weight again is going to be the mass of the ice times gravity. So let's get rid of these g's again. And we can solve for the volume of lemonade displaced while the ice is floating. And then let's think about the volume of water added. And again, we'll compare the two. So the volume of water added, just like before, it's going to be the mass of the ice over the density of water. But now we can think about something here. So the density of lemonade, that's going to be greater than the density of water because of all that sugar dissolved in it. And so therefore, we know that the volume of lemonade displaced when the ice is floating is actually going to be less than the volume of water added when the ice melts. So the level of lemonade in the glass will go up when the ice melts.